Today I will describe the relation between module categories over monoidal categories and categories of modules of algebras in those categories in certain settings. The result itself does not take so much time to describe, but I will also describe the various backgrounds. The first is a reminder. This is from 698, 657, and 658. In 698, we have talked about module categories. So this is category change this here together with a functor on if it's left module category from C times n to m, and then there is an analog associator and an analog uniter, which I don't write down in any more detail. So maybe associator. So the components are, say, A, C, C prime, and M. I will often use C for objects in C, and a capital M for objects in M. So this will be a natural family of isomorphism of this type. And it satisfies pentagon identity. Then here I have start an algebra in a monoidal category. So this is an object together with a multiplication morphism and a unit morphism, which, remember, in string calculus are denoted in this way. And they satisfy associativity and unit conditions. And then we have the notion of an A module. I use the same letter M and then rho. Rho is a morphism from, and now we talk about right modules in order to think in a sensible way. So now we have our M here, and A is acting on it, and this has to satisfy act twice. It's the same as first multiplying and then acting, and the condition compatibility with the unit. And now one relation between these is immediate, namely assume here these are the objects of the category of A modules, and morphisms are morphisms in C compatible with the action. So we have a category which I call mod A, if A is acting from the right. So assume I have an object in this category, and then we define for an object in C a functor, even which will be such an action functor. C acting on M rho is given by, as the underlying object will be the tensor product of C to M, to be precise. The M dot, the object underlying, well, if I write it like that, will be M, but we use M also for this pair, and then just the identity on C tensor with rho. And this is indeed, again, in mod A, simply because we can let A act on C tensor M by letting acting it on M. This is what we write here, and it satisfies these consistency conditions, obviously. But moreover, this gives a functor of this type. In order to get a module category, we have then to check that we have this mixed associator and uniter. Let me just write it down for the associator. The mixed associator is just the associator of C, namely, assume we have C tensor C prime, then acting on M row. By definition, here, this is C tensor C prime tensor with M, and then the identity on C tensor C prime row. But using the associator, like a missing of the monoidal category, this is the same as E tensor E prime tensor M. And then we can also write the identities analogously. And this is using the definition twice the same as C prime. And then you have to check that this satisfies the pentagon identity, but that is not hard, because we know we have just used A here, and since A satisfies ordinal pentagon, it's almost trivial. Now, if you want to go in the other direction, it turns out to be a lot more complicated already in the rigid case, but then later on I will mainly talk also about the ODVD case. And for that we have again to recall something. This is from 659, the notion of internal Hom functor for a module category. If the module category is obvious, I will omit the label M. So this is defined to be the right joint of the action functor, where well, depending on how we view this, this will be a functor from M op times M to C, or just M to C with a fixed one of the labels fixed. So that means that we have a coherent family of isomorphism between morphism and M. This one, and morphisms in C, where here we have this internal Hom object M. And in full generality, an internal Hom need not exist, but we know it exists for finite tensor categories and actually also here. And I will not only in those cases that I will talk about, but it's actually more general. Now, something that in the rigid case one usually does not talk about is a dual concept. Maybe the internal cohom. So this is a functor with the right as cohom. In index M, if we want to specify M, and this is just the left join of the action functor. So that means that we have coherent isomorphisms now where CDX on the second entry, and then we have morphisms in C where we have cohom object. of M&M prime. And again, this need not exist, but it does exist in the finite tensor case. And also the reason why one does not often talk about the internal cohom separately is that if C is rigid, then the internal cohom is just a dual. In fact, the left dual, like this order of internal hom with the order of the objects reversed. Now remember, this was in 638, the characterization of a junction via unit and co-unit. So if I have G as the right adjoint of F, then the co-unit goes from F after G to the identity. And in our case, we take, well, we have the left adjoint is the action functor, the right adjoint is the internal hom here. So we get our co-unit, but because of this, we are dealing with special situation, we introduce separate notation. And this we would maybe call the internal evaluation morphism. I write as evaluation with an underscore for M and N prime. Which is a morphism from the tensor, the action of M and N prime on M to M prime. And then one has the following lemma. If you look at the composite, where we take the evaluation, the internal evaluation for M double prime M prime, composed with the identity on the internal hom of M prime and M double prime, with the evaluation for M and N prime. And then composed with an associator such that we get the right morphism with the right domain. This gives a co-associative multiplication, which I denote by mu underscore with latest M prime and double prime from tensor product of the internal hom for M prime and double prime, and the one for M and N prime to the one for M and N double prime. And in particular, if I take all three equal here, we get the internal end of an object M of the module category carries the natural structure of an associative algebra. Also, we have the unit of the adjunction, which goes from the identity of the other category to G after F for F left adjoint of G. So this is in our case a morphism, a family of morphisms from C to the internal Hom of M, and then C acting on M, and in particular, if you take C to be the monoidal unit, then we get a morphism from the tensor unit to M, and then one acting on M via the uniter, which is no longer here. We can this will be isomorphic to M itself. So here we get to the internal end of M, which is our algebra here, and then you can check that this gives us the structure of unital associative algebra on this. The side remark, and I think it worth noting this, is the following internal Homs compatible with module functors. So by this, I mean in more detail, and this is essentially also the proof. Assume we have a functor G from M to N, which is a C module functor between C module categories M and N. Then there is a natural map from the morphisms in M, C acting on M prime, and those in N, where we apply the functor G to N and N prime. And this gives us the junctions via the junctions we get a map where we have the internal Hom. Here now I have to write the label M, and the one where we have the internal Hom for N, with G, C, Gn and Gn prime as arguments. And then via the Uneda lemma, this in turn implies that we have morphism called G underscore of internal Hom objects. So G takes the internal Hom M and from obtained from M and maps it to the one obtained from M. And then you can check that with this definition, if you now take two functors, say from n to n g and then g prime from n to p, say, then this is of course then where we get well, this will be a map this form g prime and prime, and what you can check is that it is the same as taking separately the corresponding maps for G and G prime and composing them. So in this sense, these are compatible. Next, I want to say something about module category structures on opposite categories. So let's assume that C is rigid. Then the opposite category and M is a C module. Then on the opposite category, we have a natural structure of is the left module of a right C module, actually not one, but set many, which are related by the double dual functor. And in particular, one looks at two situations, which one calls what is this symbol called? Hashtag M and M hashtag. It's much easier to write this. This is so in both cases the underlying category is the opposite to M, and then we say that here if we have that C acts on M, or maybe sometimes we write M bar to indicate that it's considered as an object in the opposite category by taking the action of the left dual of C on M, and then regarding this as an object in the opposite category. And analogously, in this case, we have put a prime here, or to be very precise, maybe one should write something like that, but I will not use that notation. A bit worse.
Sorry. For the lemma over here, do you need rigidity here?
Sorry?
This lemma on the right side?
Yes.
You need rigidity?
No. I don't think so, because if you look what I have been doing, I haven't used any structure. Maybe let me see whether I of course definitely when this was written down, it was done in the context of finite tensor where the internal homes have to exist.
Yeah.
So
so you need internal value.
You need some. Yes.
Oh.
So that gives you some condition, but it need not be full rigidity.
Okay. But you do need like internal.
Well, when I make such statements, they're just empty if these things do not exist.
Yeah.
So then it's not interesting. So I should always say I make corresponding assumptions on C. So in almost all cases, it will be sufficient that C is a finite tensor category, and then at some point we will look at a different setting when we talk about multi-variate categories, and then as monoid categories, they should also be finite. And but so in particular, this means that if I look at the linear product, again, the linear product should exist, and this is the case in the when we have finite tensor categories. Then if I look at these the linear product, then these are naturally C bimodule categories. Let me see. Now I got it wrong again because, well, it depends on how you. I should really do. I should really have it on this side. If I say no, yes, should be like that. Because on the linear product, C just acts from the left as it acts on M, and from the right as it acts here. It should be opposite, and in and then there is a lemma due to Finizzo, and in that case, certainly, I'm pretty sure that it has been. Let's assume C is a finite tensor category for all what we do in the following up to some point. That the internal Hopf functor, when we regard it as a functor from one of these, but it works also for the others too. C, the regular C module is a bimodule functor. And let me see whether I have time. Yeah, I should have time to say a little bit about the proof. Part of the proof. So let's start with the morphisms from say C prime to the internal form of M of E acting on M prime. We use the defining a junction to write this as a morphism space in M. Let me see. I double prime. And I have three. Why did I write it like that? I don't remember. But then we use the duality now to have here a morphism of here in prime, and then we use the junction again to go back to C. So we have together with the fact that we deal with the module category. And then here we have the internal norm. Makes sense. And then we use duality to bring bracket here, to bring C on the other side. BIMSA. And then by the data lemma, we see that if we apply the second argument, this gives an object which is C tensor. No, wait. Yes. With the internal home. And then by the same type of argument, you show that if you act on the first one with some, maybe I call it C prime, we see then you get a tensor from the right with the dual of C. So indeed, and these isomorphisms naturally provide a bimodule functor structure on the internal home functor. Next, not surprisingly, if you just rewrite things with left and right reference exchange, we get analogs for the internal cohom. So in particular, we have a co-associative co-multiplication from the internal cohom, say, of n double prime m to the tensor product of the internal cohoms n prime n and n double prime and prime. And in particular, the internal, I don't want to use the term co-n because the internal cohom from m to n is a co-associative co-algebra, and it's unital, while the dual of the units that we have in the algebra case. And then we have an analog of this statement about module functors giving a morphism of internal home. Now we get a corresponding morphism on internal cohoms, and then finally the analog of that internal cohom is naturally again a bimodule cluster. And now my numbering changes a bit because I added this later. So after A6, there will be A7A and A7B. Remember I mentioned in 648 the Eilenberg-Watts equivalences. In the present situation, we can learn from them that we have adjoint equivalences between Now, when I talked about it, no, I think that was in the context of finite tensor categories already. So if it's fusion categories, then we just have arbitrary functors here. In the finite tensor case, we have to look at left exact module functors. There are equivalences to the center of, and now I should again in this. I probably use a different convention concerning left and right modules than before, but let me write it like that. And also for the right exact functors, module functors, analogously to the Dirichlet center for this other module structure. Just to mention that in this case, in order to get these, we have defined the Dirichlet center for a monoidal category. And now this is a bimodule category. We have analogous half gradings, where in the equation that this has to satisfy, you not only use the associator, but both the left mix and right mix associator and the bimodule associator. I don't write that down. And in particular, when we rectify our monoidal categories, including the pivotal structure, which we know is possible, then these two structures on the opposite category on the opposite category are the same, and that you know this then by m bar. And in this case, we have simply maybe I just write this here. We have equivalences of this type, and in particular, the left and right exact functors are related by such equivalences. And 7b. Now I talk about ends and co-ends in the sense that our used this week. So we assume C is finite tensor and M is a C module, and then we define the following assignments, which I call like this. We take a functor, an arbitrary functor, a bimodule functor from, oh, I have to write it. My previous notation like that. So C as regular bimodule, and then say we take send M to the end over the module category of G of M and M. And analogously, if we have functor H here, we send it to the co-end. And these, then you see give us functors, which are sometimes called the central integration functors from this functor category. Oh, that is, here I have only the other one, and here only the other one. The H is in. So this is without a rectification. Then we have a functor from this functor category to the rental center, and obviously for the other case. And I will say something a little bit more about them later on. So last part for this first part of the lecture is now a statement. We will not have time to say much about the proof. So some of the things I introduced will not directly appear. Proposition by Ostrich, graphical result, that assume that M is a zenith indecomposable module category over a fusion category now. Then there exists a semi-simple indecomposable algebra, say A, in C, such that modules are left modules category of right A modules in C is equivalent as a module category to M, and also we may assume that A is connected or upright, so that the dimension of the morphism from 1 to A is just 1. And remember, when we say fusion category, in particular, it's K-linear over a field of that is algebraically closed. And 3 minutes. Maybe I just mentioned the idea. We define a functor f from M to C by saying we take a module N and send it to the internal home from M to N for given and we have defined M via saying that we look at the algebra which is the internal home from M to M. And then using this multiplication we have on the collection of these objects, we see actually that the home, I could have said this before, and N has a natural structure of the right A module. And then you see that actually F is a module functor. And then you show that F is an equivalence. First of all, by semi-simplicity, it's injective on morphisms. That's very easy to see. And then by a slightly more complicated argument, you see that it's also surjective, so you have isomorphisms. And you first show this for the case that N is of the form C acting on this M, but then extended to the general case. And then you next use the fact that
what's M?
what's M? M is I have chosen some object M in the model category, define A this way, and then I use this M all the time. And N is an arbitrary one.
Ah, okay, so there are multiple algebras.
Well, yes, that's another statement. Which I will make after the break probably. So we use the fact that you easily can show that any A module is a module retract of an induced module, and to generalize this to arbitrary objects. So you see that F is an equivalence, and then the semi-simplicity statement and this statement here are very easy to see. And we have to break now. I couldn't find anything in McLean's book, and I couldn't find quickly anything on the internet except that if you Google it, then you get this AI answer first, and the AI answer is a typical one. It says it's called the coend is called coend because it's a dual of an end. And I didn't ask for why is the end called end, but I'm pretty sure what the answer would be. So there was a question which is answered by the next statement. If I have any algebra A in C such that a given module category M is equivalent as a module category to the category of right A modules, then actually A must be of this form. And the way to see this is that in particular, A is an object in mod A, namely the tensor unit of it. And then you just take the internal HOM from A to A and show that, well, and then the previous argument applies. So then you get back something to M, and since you can use any M here, so no, you have to formulate it correctly, but and then. Just a remark without giving any details, and I could not give them in this case. As Ostrich already remarks in his paper, if you, instead of using algebras and modules, you use int algebras and int modules, then you can go beyond semi-simple. But I don't think that this I haven't seen this worked out anywhere. And when you deal with int objects, you have to be.
Oh, this only M has to be sent.
Sorry?
Only M has to be sent, right? Like for the.
M has to be semi-simple, yes. But then by the statement.
The C has.
No. What you know is in this way you always get semi-simple algebras in C.
Right.
And if you have non-semi-simple algebras, then C cannot be a semi-simple. But I know many non-semi-simple categories in which there are interesting semi-simple algebras, and no, to my knowledge, interesting non-semi-simple algebras. Even though certainly there should be situations where non-semi-simple algebras appear naturally in applications, even in conformal field theory. But this is, I would regard this as a kind of open problem. Next looks at some special cases. And I will be short about that. First of all, we can take the regular category, then a regular module category, then the internal HOM. We are now again back to fusion categories. Is just the tensor product, and similarly for the internal cohom. If M is vector spaces, so this is a situation where we have a fiber functor from C to vector spaces, then C is equivalent to the category of modules over some Hopf algebra in K, and in this case, the internal hom of the one simple object that we have, the tensor unit of is just a dual vector space H endowed with the natural algebra and H module structure on this dual vector space. And then finally, I don't write this down. If G is a finite group, such that the characteristic of K is not a divisor of the order of the group, so that the category of group representation is semi-simple, then this is already in this paper by Ostrich. You have classification where you have subgroups of G together with full cohomology class on that relevant subgroup. And also, if you an equivalence relation, if you have H omega and H prime omega prime, they give you the same module category if and only if they are related by the adjoint action of the group. So now we have talked a lot about algebras. Previously, we have in particular also talked about Frobenius algebras. And let me just remind you that in 674, we have introduced the notion of pivotal structure on a rigid category, and this was a prerequisite for being able to define symmetric Frobenius algebras. And a bit later, we will be concerned with symmetric Frobenius algebras. You want to say something? Yeah, about the structure on the rigid category C. This is a monoidal vector isomorphism. From the identity functor of the dual. And another concept to which I hopefully come at the end of today's lecture, but which you should know about anyhow, is assume we have C a finite tensor category and M a C module as usual. Then there is a notion of left and right relative Serre function. Which is an ender function, let's call it SRM. With the property that relative, you could also call it eternal Serre function. If you take the dual of this object in C, then there is an isomorphism for any M and M prime. It's an isomorphism. Let me see. This should be also there is also a left version where instead you have here a left dual and then another functor SL. And if you do this for ordinary homes, you get the notion of a Serfunctor. So this is a way of getting a duality in that case of vector spaces pushed into the argument, so that you have a functor in your category. With ordinary morphism spaces here, their functors directly are not so interesting because they exist only if the category is semi-simple. But then they become interesting when you go to a derived context. But not so surprisingly, if you go to this relative or internal situation, then non-trivial structures. Let me just remark that in the case that M is an exact module category, there's a relation between the Nakayama functors. This we have introduced in 649, and the relative Serfunctors. They are related by acting with what is called the distinguished invertible element, invertible objects. And in particular, if the distinguished invertible object is the tensor unit of C, in that case, to say that C is unimodular, then the Serfunctors actually coincide with the Nakayama functors. Now there is the following lemma. A finite F C module M admits a relative Serfunctor. Left and right actually, if and only if M is an exact module. And in this case, S, L, and R are equivalences. Adjoint equivalences, actually. Also interesting to know is that these functors are what one calls twisted module functors. So they are not module functors, but almost. Namely, SRM, if I apply this to P acting on M, I get an object which is not C acting on SRM of M, but instead C double dual acting. And similarly for L, then you deal with a double less dual. Actually, this also follows in the unimodular case from corresponding properties of the Nakayama functors. Then maybe this fits here. If M is an exact module category over finite tensor category, I don't write this. No, over pivot finite tensor category. So, C with the pivot structure pi. By pi. Then there is a definition due to Famitsu and Schaumann that the pivotal structure on the module category is an isomorphism by M now from the identity functor on M to something replacing the double dual, and this is precisely the right relative set functor. Such that, with the analogous property to monoidality requirement, we have didn't write what this is here, but you know what it is. If I look at pi m, the component C acting on M, then it's the same as pi C acting on pi m for M. So this will be a morphism from C acting on M to SRM of M. And in order that this makes sense, we have to compose here with the module functor constraint on, let me see, with so it can yes, remember S the S is almost a module functor, the twisted module functor, so that you have to take into account here also. And then we have the following result, again due to Famitsu. If M is indecomposable and exact, and C is pivotal, finite tensor, then a pivotal structure on M, provided it exists, is unique up to a scalar multiple. An example, not surprising if you look at the regular module category. In this case, the left exact Serre functor is just the left double dual, and the right exact is the right double dual. That you can easily check. Then the module pivotal structure in this case is first the pivotal structure of C itself. And also as a side remark, we have talked about this dual category CM star in the case of fusion categories, which are semi-simple. If instead we are in this setting of finite tensor categories, then one could define them as category of right exact module functor. Now, once you have such a pivotal structure, then you can define what Shimizu calls an internal trace. Schaumann called it something else. So again, C is exact. We denote by co-evaluation C, M. So this has two arguments. It goes from C to the internal home between M and C acting on M. The unit of the junction between the action functor and the internal home functor. And then we define internal trace on an object M as a morphism from the internal home between M and the Serre functor applied to M. And this by definition of the Serre functor is just the dual of this object. Then we can use this co-evaluation to evaluate the dual actually to go to the dual of one, which is isomorphic to one. So we get a morphism from such an object to the identity, and that we call internal trace. And then one shows that this defines a non-degenerate pairing between the internal home for M prime, say, of M, and the internal home of M and N prime. And now we come back to Frobenius algebra, again result by Shimizu, that if C I is pivotal and M is exact pivotal C module, I define pivotal structure. A pivotal module category is a module category together with a choice of pivotal structure. Then, in this case, if you look at the object in from M to M, we already know this is in general an algebra. Then this actually has natural structure of symmetric Frobenius algebra. Please see. And I don't think I should write this down. You can, for example, define this by the Frobenius form. So you take this object, use pi m. Pi m for the object M in the module category to get to this object, and then use the trace to get to 1. So we get a morphism from A to 1, and then you show that it is symmetric and non-degenerate. related results. We trivialize the pivotal structure, and we have this right module category structure on the opposite category, which I have denoted by n bar, and we also assume that n is exact as before. Then this means that these central integration functors that we have goes from bimodule functors of PC, and then one has the following result that actually these two functors are related by taking the right exact Nakayama functor for M and the identity bar and composing. And maybe I didn't write this before, but just to remind you that n in the case of monoidal categories, well, actually now of arbitrary sufficiently nice finite categories, n Nakayama functor on a category C. N, so this has this of one complex conjugate vectors for this. Then the C, which is a right exact functor, and you can think of it as the image of the identity functor regarded as a left exact functor under these Einwegers equivalences. And maybe I do not say anything about the proof here. Otherwise, I run out of time. Consequence of this is the following proposition, and we will not need this for what we are doing afterwards, but I really would claim this is an important result. So we assume that C is pivotal finite tensor, and we have two module categories n prime over C, which we can accept. Then the category of right exact module functors between M prime is an exact module over the Grindler sign. And in particular, if C is in addition a unit modular, then this is the pivotal module. And then one can define what we have called internal natural transformations and corresponding notation nut underscore between two functors G and H in this category as the internal ROM for this module category. So for this module category. for the functor screening. And this is an element in the Greenfield center of C. And as a consequence of this, one shows that together with this result by BIMSA, which I'm just erasing, that for C finite tensor and M and M prime C modules, and we assume that this is unimodular pivotal. And M and N prime are also pivotal, except C modules then for any functor, any module functor, module ender functor, M to N prime, we have an algebra where we can look at these internal natural transformations which are in the Greenfield center because they are an internal N. They have an algebra structure, but also moreover, this has a natural structure of symmetric Frobenius algebra in the Greenfield center of C. So we start from structures on C and module categories get such a thing, and actually the motivation for look at these structures came from one motivation from conformal field theory. These Frobenius algebras give objects of bulk fields and more generally defect fields in conformal field theory. And when I talked about conformal field theory, I talked about bulk and defect fields as spaces of morphisms. If you just tensor over C in that case with the corresponding simple objects, then you get an object which actually is in the Greenfield center. This tells you that you get such objects. They have the structure effect for bulk and defect fields, and this works in the context of finite tensor categories, whereas everything that is completely proven in what I was reporting is in the context of modular tensor categories. So this is much more general, and one also knows examples where one can make this more explicit. But that's not the point today. We want to know relations between categories, modules, and module categories. And in the rigid case, there is not really much more to say than this result by Ostrich. But in the rest of today's lecture, I will talk about Grothendieck-Verdier categories. And the goal is to generalize this result of Ostrich, in particular, beyond rigidity. And I have not talked this year about Grothendieck-Verdier categories before, but last year I have done that. And if you look at the table of contents, then these are the relevant parts. I do not assume that you know these things. In particular, there is only this type of content, no details. So let me repeat a bit. This will take a little bit of time in order to get to get enough information. First, let me give you a motivating example or a class of examples. Let's assume that A is an algebra in vector K, and it's enough to look at finite dimensional ones, and then at finite dimensional bimodules over A. And you see that this is in general not rigid. From this point of view, deriving many results for rigid categories seems a bit artificial. Of course, there are many good motivations for that, but this is a motivation definitely to go beyond. And an explanation of that is simply if C is rigid and C, the tensor product from the left or the right is right exact, and or also left exact, then it's actually exact because you can use the duality to relate. Relate statement that is right exact to the one that is. But already for maybe one of the simplest algebras, k of x divided by x squared. This is what many people call the dual numbers. There is one simple object of the isomorphism, S, which is one dimensional, and tensoring with S from the left or from the right, it's not important, but this is actually, you look at modules, because this is a commutative algebra, it will hold analogously for the bimodules, then this is right exact, but not exact. So this is the motivation, well, one possible motivation for the following definition. Okay. We say dualizing object and for some reason one often uses the letter K for that. In a monoidal category C is an object such that first of all for any y in C the functor of sending x to x tensor y A is representable by some object called G of y. And second, this co-defined functor G from C to C opposite is an equivalence. And then we say coordinate or in short GV category is monoidal category together choice of dualizing objects. So when this is indeed structure, we will see this later on in more detail. Let me just mention that what we have here means that we have natural isomorphisms from X tensor YK to X P of Y. And when I will quite often refer to the defining a junction isomorphism, I will mean these isomorphisms. And notation also G is then also called duality functor. Example, every rigid category is like that, where G is just a duality. Left or right. Actually, right, if we write it this way. Let me see what else. The G is a function to the opposite category. It is notably in general not monoidal, but the fact that the ender functor from C to C obtained by applying G twice is monoidal. Well, G and G bar to be precise. And then importantly, we have the following definition of a functor, which I call blob or something, from C cross C to C, where X blob Y is defined by applying the inverse of G to G of Y and G of X. And in this case of a rigid category, this just gives us back factor isomorphic to the tensor product. And finally, not finally, maybe I can say a little bit more. If we have a structure C and one and associate us the NK of GB category. Then there is a second GB category. We take the same underlying category called C prime and take this block as a tensor product. And you can check that this has the property of a tensor product functor. And then K as the monoidal unit. And then we have an associator and unitas for this structure. And then there is a dualizing object, which is just a monoidal unit for the original tensor product. And you can leave these actually in terms of the associator and unitas here. I just write it for the associator. So if we have object X, Y, Z, then we get the associator by taking the inverse of the associator for the original tensor product for the object Z, G1, Gx. Again, like and last thing before the break. Why do we call this a duality structure? Well, by direct calculation, you see that for morphism spaces of this type, you have an isomorphism to morphism from X to Z, and then this block tensor product with G of Y, and also to the morphism space to this Okay, the other tensor factor y, and then g equals no. That's that, which means that in an important aspect, G behaves like a right duality and G inverse behaves like a left duality. Okay, and then I will say more about this after the break. Yeah, Okay. So next point. So indeed, the choice of dualizing object is structure. And as shown by Boyachenko and Drinfeld, actually G and G inverse furnish an equivalence between the PK groupoid of C, so the subcategory generated by the invertible objects, and the full subcategory generated by the dualizing objects. And from this it follows, for example, that if you have an invertible object U, then you can write G of U as K tensor with U inverse, and similarly for G inverse. And in particular, then also G squared applied to U is invertible. Well, that follows already from the fact that G squared is monoidal. But in particular, this means then that the dualizing objects of the category I start with are the invertible objects of the category with the other chemical product and the other way around. Important for us is the following. We have two tensor products. None of them is preferred. So in particular, we should also look at mixed tensor product where we use both of them in multiple tensor products. And this gives rise to the notion of what is called distributors. It turns out, and the full proof is actually relatively new, I would claim, that there are in each Gründlich-Verdier category natural families of morphisms from X blob Y tensor with Z to X blob times with Y tensor with Z. So we take out the blob product to the left, and also you can take it out to the right in this form. That then you call delta L. And so then you get X tensor Y blob Z. And notably in general, these are just morphisms, not isomorphisms like associators are. And but similarly as associators, these satisfy pentagon identities, and in fact 6 different ones, 2 for delta R, 2 for delta L, and 2 which mix them. And I will not write them down, but mention generalization, which I also will not write down, but it's a good exercise to write them down by yourself. You simply have to look at the various possibilities when you have 3 choices for tensor product, either blob and times, then going from one bracketing to the, so to say, opposite bracketing in the same sense as for in the ordinary pentagon. You can do this in 2 different ways, and this gives you a pentagon, and they are have to be satisfied by these. And finally, Gründlich-Verdier module categories. denoted by M and action of C, just as before. And we define them as homoloidal categories, except that we have an additional requirement. And remember, when I introduce monoidal category, I did this twice. First for general module categories, first for general monoidal categories, and then for the special case of finite tensor categories, where there was an additional requirement. And this is a generalization of the latter, namely, we require that the action functor, so either considered as an end functor of M or considered as the functor from C to M. These have a right adjoint for any C in C and for any M in any respect. And this guarantees that HOMs and co-HOMs exist, but actually HOMs still exist for the ordinary tensor product and co-HOMs for the other tensor products. Note, however, that we do not use in the definition the fact that we deal with a Enigma category. Only then we will have these two statements in the way I just made them. But it turns out to be that this is the right thing to do. And also in the case of finite tensor categories, it reduces the definition from the Ettinghoff et al. Book that I gave before. And once we have this, maybe an example. If you look at the regular C module, where we just use the tensor product, then we will get, well, in the same way as usual, we get a module category. And in this case, the functor, which I will denote by HC, which is just the right adjoint of the action functor here, which by definition has to exist. In this case, this can be given explicitly as applying G inverse to C and then acting in tensoring with the other tensor products. And next, I'm using this notation now for an arbitrary just this notation. Now it's in the situation for an arbitrary module category. We define an analog of the second tensor product, second action, which I now can pronounce at all, which sends Cm to C new action on M, defined as taking this functor here for G of C and applying it to M. And by definition, because of this has a left adjoint in each variable, and therefore it defines the block module category structure. And this is defined by just the dual version of that. So we say that instead of right adjoints, we require left adjoints. And also, so here we get from one action, we get another action, and then remember we had on the opposite category of a module category a right module structure, and then they get right both ordinary action and new action. Structures or in the opposite category. But just and you can give them actually explicitly, maybe I said, because it shows that when you go to the opposite, as you should expect, things are turned around. So you have a right action from M op cross C to M op, and another right action of the same form. And in this case, C is mapped to G inverse of C with this other action on M, and here it's mapped to G inverse of C with the first action. Then via the unit and co-unit of the defining a junction, one gets analogs of evaluation and co-evaluation morphisms of the following type. But in addition to what we have from the internal homes, but we will see a relation. There is a relation which maybe so these are morphisms from this combination to M, respectively, from M to this combination. And these sets, we call them evaluation and co-evaluation because you can check that they satisfy snake identity. Also, there is bijection. I don't say this explicitly. I don't write anything between Lux module functor structures for this action and op-Lux module functor structure for this action. But now something which I did not come to at all last year. These are module distributors. Just like for the adjoint, for the regular module, we have the distributed. We have an analog, an arbitrary module category. I had not erased the formula and recycle it. So these are morphisms. I now take use X and Y for objects of C. M no time. M as before. So here I just replace the object places tensor product by actions. If I start with morphisms of this form, and actually one can.
So on the right hand side, on the top row, would be X tensor Y.
Right. And again, they are in general not isomorphisms, and we can define them now in the previous case. I just told you they are there, and one can argue about that. But here, with the definition of module category that I gave, we can actually define them via the Oplats module structure function. Structure. On the functor that is given by C, sending to C, acting on M, that gives us delta R, and this exists. Well, the functor has such a module structure, functor structure by definition, and analogously for delta L, you would take the Lux ordinary action or first action module functor structure on C maps to C leg action on M. And by then, one has a result, and these satisfy 6 pentagon identities, namely the 6 that you can write down independently, 2 for delta L, 2 for delta R, and the mixed ones. And for the regular module category, the module distributors reduce to the distributors, and these pentagons reduce to the pentagons. Detailed proof of the case for Grothendieck-Verdier categories themselves goes via the proving this here in so much more generality. And then let me mention that using special cases of the defining the junction isomorphisms, one gets what one calls Grothendieck-Verdier evaluation morphisms. Then now just one label from Gx tensor x to k. But this is like for a rigid duality where we go to the tensor unit, but now it's k, and analogously a left one. And corresponding evaluations. That we get snake identities. And the snake identities, I don't write them down, but they involve distributors. The ordinary snake identities involve associators, but we usually do not write them. Here we have to write them because they are not isomorphisms. And just because they are not isomorphisms, it's a priori not clear whether the distributors go in the right direction. But they always do. Many things you would naively do by forgetting that they are not isomorphisms actually work very nicely. And then I already said that we will have internal homes and cohomes. And for the internal homes, we use the first action, and for the cohomes, the other. And they exist because of this requirement in the definition of module category. So home internal respect to M then is the right adjoint, which by definition exists of the action functor, the internal co-hom is the electric joint. I'll try to find here, but it must be wrong. Yeah. And you write down the corresponding ISOs. And then one shows that they are actually related in a way analogous to what you have for the rigid case, except that in that case, this is a reason to talk only about one of them. But here you have these two different actions. So they have the internal co-hom for M prime is actually isomorphic in inverse applied to the internal hom from M prime to F. Then again, similar to the case of an ordinary monoidal category, you have via the units and co-units of the function, you have internal evaluation morphisms. Co-evaluation goes to the co-hom with the other action. And these give you multiplication morphisms. U underscore M prime and double prime of the same type as before, and co-multiplication. Are defined dually, where these involve tensor products and actions, and these involve the other tensor product and the other action. Then in particular, this is an important motivation for the definition that will come. If we take M equal to N prime, then we get an algebra, respectively co-algebra structure. So hom, internal hom from A to M. We tensor as an algebra, naturally, and the internal co-hom naturally co-algebra for, however, the other tensor product. And analogously, when we have two different arguments, then let's call this in the following to save time A, M, and this is C, M. And for any M prime, hom M prime is naturally AM module and co-hom of M prime M is naturally CM co-module. And in the special case of the regular module, we have that internal home of CC prime is isomorphic to T. The C tensor E inverse C prime, which by definition of the block product is nothing but C prime. And similarly, the internal column is isomorphic to C, and then all the first tensor product we call the C prime. And then there is an analog about the statement that these are bimodule functors. If I act with C in the first variable and with C prime with the other action, second variable, then this is isomorphic to C prime, and then the block product to the original internal home block with this is C prime, and here I have C dual. No, it's C dual, it's not G, really. And analogously for the cohom. The roles of everything on what one is. And from this, it then follows that we have natural weak module functor structures on the internal hom and cohom when we think of Gen S functors from M op tensor M to C. Well, let me just write the result that the internal home is a Lux module functor structure with respect to the first action, and a strong module functor structure for the other actions. And also when we take the internal home but fix the other argument, then this is a Lux module functor structure for the right action on the opposite category. And if you do analogous things for the cohom, then just the role of the two of Lux and oplux is interchanged. So now I'm finally in the position to talk about GV for linear algebra. The GV algebra in a Grothendieck-Verdier category is just an algebra in C with the first tensor product, and this is motivated by this result. And then by the second result, we say that the GV co-algebra is a co-algebra, but now in C with the other tensor product. And then the GV Frobenius algebra is, of course, GV algebra. And the co-algebra with a compatibility condition, which now reads as follows. With detailed U blob identity on A composed with left distributor composed with the identity answered. The original tensor product with A is equal to co-product after product, and it's analogous and equal to identity blob U composed with the Y distributor. No. What did I write here? This and yes, identity A, B. And this looks essentially like what we have in ordinary covariance algebra. So you might be tempted to draw this in terms of string diagrams. So the first left-hand side would look like this, except that now here you deal with in this region you deal with the first tensor product, and in this region with the other one, and you have to would have to use an associator normally, but now we have to use a distributor maybe delta L, and in the middle part we just have this situation, and on the right we have this turned around where we then have the right distributor, but this is actually not really correct, because it turns out that for Grothendieck-Verdier categories, unlike for monadic, there is no complete coherence theorem. And the coherence theorem is a necessary ingredient for using Shanghai. However, still something is true, and I'm not able now to tell this in detail. I'm not sure whether it has been understood in full detail, but the second point is you can still just draw as an intermediate set these things and get an idea on what should be correct. And then in this situation, it works perfectly. In other situations, you only know that you should use to manipulate the diagrams some combination of the distributors and associators, but which is not clear because of this lack of full coherence, and then you have to work.
So it's the lack of coherence between associators and distributors. So these
yes.
the associators themselves are coherent themselves.
As long as you only have associators, there is no problem. As soon as I think there's a statement, even if you just have associators and distributors, it still works. But as soon as you have uniters, no longer works. And I have not for everything here, because I suppress the 1 and k line. And these involve the uniters, and therefore it doesn't work directly. But what you still have, at first, is the following lemma. There's a bijection between GV algebra and GV co-algebras. And this goes just by the factorality from the G and its inverse. And the idea is if you have an algebra, then we define a co-product as follows. We start from G applied to A, apply G of mu to get to G of A tensor A. And then we know there is an isomorphism to GA block GA. And then we take, we see that the associator for mu actually, associativity for mu applies co-associativity for this map. And also the co-unit similarly you define via the unit. Also other statements generalize, but I will not tell you write down anything because otherwise I cannot come to the main result. But let me mention that of the two equalities that we have here, only one is independent. In this case, it's rather hard to prove this actually. There is a proof using a certain three-dimensional calculus for that. Then again, every morphism of Frobenius algebras, meaning algebra and co-algebra morphism, is an isomorphism. So we deal with groupoids, and then there's a second definition via the analog of a non-degenerate invariant pairing, except that the pairing now goes not to 1 but to k. And the variant of that, you use what is called a Frobenius form. So in an ordinary case, it would be a morphism from A to 1. Now it's a morphism from A to k. And but the way these are related is precisely like in the ordinary case, except that whenever the co-algebra structure is involved, we have the block tensor product, and you have to insert distributors. Also, you can, like for rigid categories, you can define the notion of a pivotal Grothendieck-Verdier category. It's the definition as one gives it looks a bit different, but it's actually the same, except that you have one additional requirement, namely the K component of the pivotal structure. So this is morphism from K to G squared applied to K has to coincide with a specific morphism that you have, which follows directly from the definitions. And then once you have that, you can introduce the notion of Nakayama automorphism in the same way as for ordinary Frobenius algebras. And then the symmetric Frobenius algebra is Frobenius algebra for which the Nakayama is trivial, is the identity. But now, first part of the relation, which is easy to prove, but I will not say anything about proof. If G, well, I will say a little bit. B is a GB category with equalizers. Actually, not all equalizers must exist, but natural to require that. And A in C is an algebra. Then the category of right A modules is naturally C, GB left module category. And also, let me just write delta LR for this category, module category, are just the distributors of the monoidal category itself. And what you have to show is that, well, you can define a candidate for an action, just as in the ordinary case. You have to show that in both variables you have right adjoints, and that to do, we define candidate tensor product on co-modules, where we use the relation between algebras and co-algebras, and then this extends to modules and co-modules over them via an equalizer, which is just the dual version of defining the ordinary tensor product over A as a co-equalizer, and then use the inverse property of equalizers to show that the action function actually has a right adjoint, which is simply given by the internal one. And similarly, for the other action, and you have and then this way you whenever you have a let me see. Yeah, for the to show that this has a right adjoint, you have to show that when you have a right A module structure on M, then on D block M you also get a right module structure. Time is over. Let me see what I can say. Maybe I have to continue this a little bit next time, because the main statement is missing. Let me use 1 or 2 minutes to introduce some necessary. So this direction is again easy. The other direction is more complicated, and in fact, the statement itself is more complicated than in the ordinary case, and you need more concepts. And let me just introduce them. There's a notion of C generator of the module category M. Everything is now called the Gaudier module categories. This is an object in M such that for any object M in M, there is an object C in C together with an epimorphism from C acting on M0 of that. And analogously, there's a notion of the co-generator, and the N0 in M such that for any M in M, there is a C prime in C together with a monomorphism from M to C prime with the other action on M. And you can easily check that This is then used in the proof later on. If you look at this module category that you get here, then the algebra itself is a generator. Where the relevant epimorphism is just the representation morphism. And maybe I should stop here. Time is over.